Okay, so yeah, once I get this in my email after lab, I'll post it to Blackboard. Yeah, so this quantity capacitance that we're going to be talking about in this lab is kind of, at least to me, like super mysterious. Of course, you can just take these equations and run with them, but it turns out the C, the capacitance, is just a constant that we define, that allows me to say that the electric field of a capacitor is defined by this equation, and it's defined by this equation. Not exactly this equation, and I'll explain that in a second. That's not right. Okay, so I'm going to start with the idea of the first equation from lab 1. Let me get rid of this floating meeting controls. Okay. So imagine that we have these two plates. It's very similar to lab 1 where we had the voltage on one thing. Let's see. How can we make sure that everyone is muted? I hear like a bunch of feedback on my computer. So we have like this voltage quantity that like if two of the voltages, I guess I can just turn my volume down. Does that work? Okay, yeah, that works. So we have two voltage quantities. This is kind of like our high voltage and our low voltage from lab 1. And I'm going to define this. All these definitions here are just to match up with the lab manual, which just gives me, where is it? V's. So this V is the difference between the parallel plates that we have from lab 1. And imagine that the parallel plate has an area. I'll call the area A. And I'll say that the total charge on each of the plates is plus and minus Q. That's from, right, that was kind of the result of our lab 1. It was, one of them was a Q and the other one was supposed to be exactly opposite with a minus sign, the same magnitude. And I'll define this thing called the charge density, which is, it's actually not in here, but it's very helpful. So it's the charge density is the amount of charge over a given area. So if I block off this region with my mouse and I know the area of that and I know the charge, then sigma, this little symbol right here, is the charge density. So in other words, I can say that this plate has a charge density of plus sigma, and this one has a charge density of minus sigma. V, again, is the difference between the two. And to link up with the lab manual, I'll call the delta X from this thing, remember from lab 1, I'll call that D. So now I have that the electric field is from the delta V over delta X is V over D. The reason why I'm not including the minus sign is because I already know the direction. From lab 1, we know that the electric field points from plus to minus. So there's no reason for me to include the negative. I know where it points. And now the kind of theoretical jump that allows us to talk about capacitance is something called Gauss's law. It tells me that the amount of E field, so like the number of lines, I guess, on your dipole drawing and the capacitor and the parallel plate drawing, the number of lines that goes through a particular area, I'll call this a Gaussian surface or a Gaussian pillbox. So this is my particular area that I'm talking about. The amount of electric field lines that go through that area is equal to the charge enclosed with some constant here that's called the permittivity. If we were working in a vacuum like we do most of the time in class and stuff, we talk about the vacuum permittivity. That's how easily charges move through empty space because space isn't really empty. And if we wanted to talk about some material, like what we're using in lab, we're going to use E instead of E naught. This is vacuum. And then E or epsilon is just the permittivity of that material because every material is more, is harder to move through than empty space. So thinking about this equation, this says that if I integrate E over that area, so E is like the number of field lines that is going through each of the areas. I know that this is a plus charge, so I know that the E fields go away from it, both up and down. And so the number of arrows on one side is exactly equal to the number of arrows on the other side. So I have a 2E. And just from, I guess, vector calculus, if you integrate an area element, this is an infinitesimal area, it's the, like an area block, I guess, that just turns into the whole area. So now I have 2E, the area of my Gaussian surface, Q enclosed. And if sorry, I skipped this part down at the bottom. Q enclosed, I can determine based on my sigma, the charge density. If I want my Gaussian surface to have, I'll call it A enclosed, the charge enclosed on that is multiplying it by the density. So if you have the area and the density is a unit of charge over area, then the Q enclosed is multiplying those two, right? This is charge over area, this is area, so that gives me the charge. So now both sides of these equations tell me that Q enclosed sigma A over epsilon and 2EA. Now I can cancel out the A enclosed on both sides, and I'm left with the electric field of a plate. It's the exact same for a negatively charged plate, just with a minus sign, because everything's pointing. These two arrows right here are typos. They're supposed to be pointing up towards the plane, right? Because a negative charge, the electric fields are pointing towards it, and the positive charge, the electric fields are pointing away from it. So now let's talk about two plates. We can do this just by drawing lines. At first, we can draw lines for the plus one. We have, let's just draw two for each plate. We have two going up, two going down, two going in, two going in. But the fancy thing about this equation, there's no R. So unlike the dipole that we had from before, where it fell off as you got farther away from it, this does not. So these lines from the plus go all the way down the page and all the way up the page. So these two lines are also down here. And the same thing happens with the minus. So the electric field on the top and the electric field on the bottom exactly cancel, because this one is just a minus sigma over 2 epsilon, and this one is the plus sigma over 2 epsilon. And in the middle, they multiply by 2, because the electric field on the plus one is going down, the electric field on the minus one is also going down. So the electric field between both of them is just sigma over epsilon. Again, I'm not including the direction because I know what direction it goes. It goes from plus to minus. Now, if I write this out with my equation from the first lab, I have E is V over D. And I also know now that this, so when I say that the capacitance is the relationship between this equation and this equation can be derived formally either with the Newtonian stuff that we did last time, or in lab one, where I talked about forces and potentials and you know, did some derivatives, or you can use Gauss's law, this thing. It follows exactly, it's the same thing. So what I meant was that you can either talk about this potential formulation or Gauss's law, and as long as you define the following thing. So I have E is V over D, or sigma over epsilon. I know that sigma is my charge density. It's just Q enclosed over A enclosed. So if I fill that in, I have VD from this one, Q over A epsilon. And then I isolate for Q, just like, oh, wrong lab report. I mean lab manual. I want to mimic this equation. And so if I mimic that equation, the constant that allows me to say that that equation works is just called the capacitance. It is a physical thing, but as a theoretical construct, that's all it is. It's a because if look at the units on all of these things, the permittivity of the space is constant. The area of the capacitor is constant. It's not like my capacitor is changing size or anything. And the distance between the capacitor plates is the same too. So the only thing that's changing is the charge and the velocity. I mean, the voltage. So it's just the proportionality that allows me to go back and forth between the two things. A little bit more practical, I just want to talk about circuits because that's what we're going to need to use throughout the lab. A circuit that's in series means that you have two elements. So here, this is like a battery or your power supply in the lab. This is a capacitor. You draw it like that just because you know it's kind of what it looks like, a gap where charges can be separated on, or in parallel, which means that they're kind of like there's a split in the route. Charges can either go this way or go that way. The main law of circuit stuff is called Kirchhoff's law. It says that all the voltage supplied by this battery or the voltage supply is exactly used by the elements in the circuit. So by that, I mean, if this is a plus, this is let's say this is +2, this is -1, and this is -1. So they have to add to 0. So if you go in a loop for this series diagram up here, the drop or the potential supply from this is equal to the potential drop here and the potential drop here. Or in other words, you can just add them all together and they get 0. In parallel, it's a little bit more complicated because you have two loops. You can either go here or you can go here. Oops. And go around that loop. Or, I'm sorry, that's not the right loop. This loop or this loop. So now that we have two loops, I'm going to call this voltage supplied V1, this one the drop across this capacitor V2, and the drop across this capacitor V3. I know from loop 1, Kirchhoff's law, it must equal 0, so I add those two, it's equal to 0. And for the second loop, I add them and they're equal to 0. If I cancel the 1s from each of these equations, I know that they're equal to each other. This doesn't mean that the capacitance for each of these things is the same. The only thing that's true is that the voltage drop across both of them in parallel is the same. In particular, it tells me that neither the charge nor the capacitance needs to be equal, only that these need to be equal. So these, the capacitance and or given the capacitance, because, you know, usually we'll say, okay, this is 2 microfarads and this is 10 microfarads. The charge distributes in this parallel thing according to the fact that the two voltages are the same. If I wanted to relate these two capacitance, like how can I make some relationship between both of them? I would do the following. What if I viewed it as one element? So I took these two things and imagined they were just one capacitor. Then I can talk about using this equation. I can say the total capacitance is the total charge and the total voltage. Also, I know that the two voltages are the same, so I can write it in either way I want. When I write V, I'm just a shorthand for either of them because they're both equal. And V and Q total is the charge on this capacitor and the charge on this capacitor, 2 and 3. And then I can divide each of them by V, respectively, 2 and 3. Again, they're the same. And then I have that in parallel, the total capacitance of this element right here would be both of them together. It's actually a bit more complicated for series, and that'll be one of the discussion questions. So equation 3 is insanely confusing, so I hope this helps you. I think the notation here is really hard to understand. We just derived 4, but 3 is a little hard to understand. So what you're going to be doing in the lab is you're going to be charging one of the capacitors. So instead of this circuit, imagine you cut that wire and you cut that wire so that you're just charging this thing. And that's it. So you supply the charge to this capacitor and then you cut the voltage supply off. So all the charge that resides on this capacitor, that's all you get. So in terms of what is done in the, I think it would be better if they just said Q total, V total, and C total. but for some reason he says V0 and C1. I don't know why, but that's what it is. You can just think of them as totals. Now, what if we connect this capacitor to this capacitor? The charges are going to move because the charges always reside. Like charges don't stay in the wire. They reside on the surface of a capacitor. But there's no more charge to be distributed anywhere. So the charge from this setup is just distributed over both of the parallel plate capacitors. So you're just dividing the charge of all of it into each of the things. Ignore this scribble. I was confused about how to derive that. So what I'm going to say is that the initial Q, the Q that comes from charging it, the total, is equal to the final Q, which is the charge over both of the capacitors. So I'm going to call this Q1 and Q2, which by this equation is C1 and V2. But because they're in parallel, I know that V1 is equal to V2. So I can call that V1 or V2 respectively, factor it out, and then I have this thing called C1 plus C2, and I guess just V, or I guess as they call it in the lab manual, they call it V parallel. And right here is what we already derived. So again, I think this is done in the wrong order. You should derive 4 before 3, because we have 4 right here. And so that's what that means. Now there is a very in-depth, there's a lot of theory behind this device right here, and this equation tells you practically nothing about it. The more helpful thing is here. Even that isn't great, so I'm going to head over to Wikipedia to show you the real equation. The kind of pivotal equation of an RC circuit is that the voltage, I guess like if this is the voltage that's supplied by your battery in an RC circuit, and by RC I mean there's a resistor, so something that charges like struggle to get through, and a capacitor where charges reside on it. You have each of these at your lab station. And it tells me that the voltage in this circuit will drop as time goes on. So T is time, and this little tau that they do define in the lab manual is R over C. If I plot this thing, it tells me that the voltage starts at whatever my battery says. So let's say my battery supplies 5 volts. And here I'm just plotting this thing here. I'm just ignoring the RC. RC is just a constant, doesn't matter. And I'm just saying, I'm giving it a number so that it doesn't start at infinity. I'm just saying 5 volts it starts at. And T is a time, so I'm going to start it at 0 seconds and end at 5 seconds. This exponential, that's what an exponential curve looks like, the e to the negative something. It falls off to 0. So in an RC circuit, you start off at some voltage, and then it drops to 0. The interesting thing about this is not at all mentioned in the lab report. It's really a relationship between something you did in 133. In 133, when you, let's see here. So there was no piston in 133. It was just 2 springs attached to our mass, and we were, pulling it apart and letting it go through the thing. But imagine there was a piston. The piston is what we'll call a driving force. And imagine, unlike in 133, where we had a frictionless plane with the air hockey type thing, imagine that there is friction on the surface. Or you can equivalently think about air resistance. So what this is called is a driven, hence the piston. The piston is moving back and forth, so making the spring move. Damped, which means it's subject to some friction or air resistance that's making the mass move less than it could. And harmonic oscillator is just the spring. There's a super deep connection between an RC circuit and a damped harmonic oscillator. And I find these Wikipedia articles in particular to be really helpful. This one isn't particularly helpful, actually. There's kind of annoying units there. This one is just called system equivalence. And it talks to you about the equivalence between an electrical circuit thing, where the current is the charge going through the wire. Voltage is what's applied. Again, so voltage is like, is kind of like the force. It's what's being supplied to your charges to make them move. Let's get rid of this one. It's kind of annoying. It does go way more into depth, but this one's totally sufficient. The spring is kind of like your capacitor. You can ignore mass for the moment. It's too much to explain at the moment. And then damping, like this friction or air resistance, is like a resistor. A resistor is something that prevents charges from moving too quickly through it. And it's not one of the discussion questions, but I'm going to make it one of them. I'll write it on the board, but it's basically how can you relate this equation and what you see on the oscilloscope. So what you'll see on the oscilloscope is it's a mix of, this is one of the things you'll see on the oscilloscope, and another thing that's helpful to think about the discussion question. This is for the RC circuit one. So what you'll see on the oscilloscope is this function superimposed or added with another function. And the key to the discussion question is how that relates to, how an RC circuit relates to a damped harmonic oscillator. So that's all the theory I had. I know that was, like 23 minutes. But this lab is like, I found these equations incredibly hard to understand. And I'll just go, now I'll start going back and forth between the classes and, talk about some of the tips and tricks I wrote on the board. Oh, there was chat. I'm sorry. So when I hide the floating meeting controls, oh, okay. It's, yes, they will definitely be posted, to Blackboard as soon as I get the recording after class. It will it'll just like be sent to my email, and then I'll send you guys the link to it. Yeah. Sorry, when I do the hide floating meeting controls, I can't see when chat comes up. Okay, so I'll stop the recording now and start heading over to answer questions.